register is a small high-speed storage unit within the CPU. Data undergoes processing not directly within the computer's memory, but is first loaded into a CPU register where further operations can take place. For example, if you want to add two numbers together, you might first load the first number into one register and the second number into another, then perform the add operation, storing the result within a third register, and finally copying the result from that register into memory. A 64-bit program running in user mode on an ARM processor has access to 31 general-purpose registers, a program counter, and a combined 0 register/stack pointer. Registers X0 to X30 are general-purpose and you can use them for anything you like. In the example before, we could have stored the first two numbers in X0 and X1, with the result being put into X2. While these registers are general purpose, it's important to note that some of the registers in that range do have a standard agreed upon usage, such as X30, also known as the link register, being used to store the return address of a function. Although the registers can store 64 bits, we don't always need that much. Often you'll find that 32 bits is enough. All the X registers can be used in 32-bit mode by referring to them as W0 through to W30 respectively. When this is done, the lower 32 bits is used, with the upper 32 bits being zeroed out. With that out of the way, let's write our first program in assembly. Taking the classic Hello World program, let's see how it would be written in ARM 64-bit assembly. Assembly files are specified using the .s extension. Let's create a file called hello to hold our code. Let's start by writing a top-level comment documenting what the program does. Assembly is archaic, that's why it's so important that we document our code. Keeping track of which registers are doing what becomes important as our program gets bigger. Let's define the entry point of the program. The assembler marks the label containing _start as the program's entry point. It's for this reason that it needs to be defined as a global symbol so the linker has access to it. Like a main function, there can only be one occurrence of start. Before we start populating start, let's define a section to contain our program's data. This is done using the .data identifier. The data section follows the format label, data type, and data. In our program, we're storing the string hello world as ASCII under the label message. With our data defined, let's learn about the three instructions we'll see today. The move, MOV instruction, is used to move data into a register. The load register, LDR instruction, is used to load an address into a register. And finally, the supervisor call, SVC instruction, is used to make a software interrupt. It switches from user mode to supervisor mode, allowing the execution of privileged instructions or accessing system services. Now that we understand what the instructions do, let's finally get to making our Hello World program. The first thing we want to do is write our string to the standard output. This can be done using the write syscall. The write syscall takes in three parameters: a file descriptor, the buffer to write, and the length of the buffer. Looking at the syscall docs, register X8 holds the instruction number, while registers X0 to X2 hold the syscall parameters. Using the move instruction, we can store the value 1, which represents standard out, into register X0. 1 is prefixed with a hashtag because it's an immediate operand, also known as a constant. The second parameter requires an address to the buffer. We can load the address of the message variable into register X1 using the load register instruction. The third and final parameter requires the length of the buffer. Using the move instruction, let's put 14 into register X2. With the parameters loaded, let's move the value 64 into register X8. Looking at the docs, we can see that the write syscall is associated with the value 64. Finally, let's invoke the syscall using the SVC instruction. Passing 0 specifies the default calling convention. And with that, we have a completed invocation of the write syscall. The final thing we want to do in our program is exit. Looking at the docs, the exit syscall takes in a single parameter, the exit code, and is associated with the value 93. Following the same format as before, let's write the assembly code required to execute the exit syscall. We now have a completed Hello World ARM 64-bit assembly program. To execute this, we first need to call the AS command to translate assembly code to object code. We can then call the LD command to link our object file and create an executable. Running this, we can see the string hello world output to the terminal. You can find the code along with further resources used during the making of this video in the description. If you have any questions, feel free to leave them in the comments section, as well as liking and subscribing if you enjoyed the video. Thanks for watching.